Lesson 5, it does not have a checkpoint, so I will be doing every other workbook. So, question 10. Use the polygon to answer the question. So, first thing I noticed about the polygon is it is a regular polygon because all of the sides have the same tick marks and all of the angles are marked the same as well. So then the question is, what kind of symmetry does the polygon have? And so using the theorem review, I'm going to look for symmetry. That's symmetrical, not symmetrical. It says, in fact, for any regular polygon, the number of lines of symmetry is equal to the number of lines of its sides. So this has 1, 2, 3, 4, 5, 6. It has 6 sides, so that means it's going to have 6 lines of symmetry. And it is through each of the vertexes. So if I drew a line through the vertex D, and if I could keep it straight, there's a line of symmetry, and you could do that for each vertex. And then if I'm looking at, if I keep going about rotational symmetry, it says regular polygons have rotational symmetry. Okay, so that was pretty blunt. So it has line symmetry and rotational symmetry. So we're going to move to question 8. Use the graph to answer the questions. Okay, so we have a pentagon A, B, C, D, E, and pentagon A prime, E prime, D, A prime, B prime, sorry, A prime, E prime, D prime, C prime, B prime. I was looking at it in a clockwise rotation, and so that's why I read it A prime, E prime, D prime, C prime, B prime. And that's a key to me that something happened with a reflection. Okay, so which series of transformations correctly maps polygon A, B, C, D to polygon A prime, B prime, C prime, D prime, E prime? This is pulling on the information you learned back in lesson 3. So I'm going to go back to the lesson 3 and use that as a reference for this. So it says a translation of 4 units up followed by a reflection in the y-axis. So let's try that. If I moved A up 4 units, 1, 2, 3, 4. So there's 4 units, and then it says followed by a reflection in the y-axis. Well, the y-axis preserves distance to the y-axis. So this, how I'm going to check if it reflected it in the y-axis is I'm going to count. It was 1, 2, 3 units away from the y-axis, so I'm going to count now 3 units to the right of it. 1, 2, 3. And yes, that is exactly where that point would land with a reflection in the y-axis. So let's check B. So again, we're going to count up 4 units. So then it's 1, 2, 3, 4. So that's where it would be, translated it up 4 units. And if we were to reflect it about the y-axis, it would need to preserve that distance. So this looks like it's at the halfway, so a half and 1 to the left of the y-axis. So now I'm going to reflect it on the right side, so it should be 1 1/2, which it does land right there. So let's check C, 4 units up. 1, 2, 3, 4. That's where the 4 units up would be. And I'm going to check the distance. So from the y-axis to the left to where that translation up 4 units is 1, 2. It's 2 units to the left, so now I'm going to reflect it to the other side. It should be 2 units on the right, and it lands right there. And then let's verify D. 1, 2, 3, 4. So this is where D would be, translated 4 units up. And let's count the distance. So it'd be 1, 2, 3, 4. It'd be 4 units to the left. It is 4 units to the left of the y-axis. So now when I reflect it, it's going to be 4 units to the right. So it's going to be 1, 2, 3, 4. And it is exactly right there. And I'm going to let you know what maybe this thought came in. Do I have to check every single point to say yes, it was translated up 4 units and followed by a reflection in the y-axis? If the transformations are rigid transformations, no, you could check 1 point and be finished with it, because rigid transformations preserves the same size, so the same distance and the same shape, so it doesn't change anything. It just basically picks up that image and moves it somewhere else on the coordinate. And so right here, I would note this. Rigid transformations preserve angle measures and distance. So it is the same size and shape as the pre-image. And what are the rigid transformations? Well, rotations are, reflections are, and so are translations. And it's also listed right here at the very top. Rigid transformation. Translations, reflections, and rotations are all rigid transformations. So again, I could have checked A, since I know a translation is a rigid transformation and reflections are rigid transformations. I could have stopped after I had verified that A landed on A prime, and I could say, yep, that is exactly the one that we want. So that's another way you could go about answering it, is if you remember what your rigid transformations are and what they do. So there's question 8. And the quote for this video lesson is an anonymous quote, and it says, "Years may wrinkle your skin, but lack of enthusiasm will wrinkle your soul." So have some enthusiasm in your life to keep that soul bright. So question 6, it says, use the graph to answer the question. Which series of transformations correctly maps trapezoid ABCD to trapezoid A prime, B prime, C prime, D prime? A dilation with a scale factor of 2 about the origin, followed by a reflection in the x-axis. Okay, so since a dilation is not a rigid transformation, we are going to check each point until there's a point that doesn't match the transformations listed. So the first one that we're going to do is we're going to do a dilation with a scale factor of 2 about the origin. So point A has the coordinates of 1, -1. And if it were to have a dilation of a scale factor of 2, we multiply each coordinate by the scale factor. So I'm going to take 1 and multiply it by 2. 1 times 2 is 2, and negative 1 times 2 is negative 2. And there's our dilation, and then it says followed by a reflection in the x-axis. Okay, so reflections in the x-axis are going to keep the x-coordinate the same, 2, and they're going to change the value of our y-coordinate. So negative 2 would become positive, so it changes its sign. So there's one way we could check. So a prime should be at 2, 2 if we followed this transformation correctly. So over to up 2. So is this where a prime is at? No. So there's one way to check it. The other way to check it is to do the dilation with a scale factor of 2, and we could say, okay, so here's our second way to check. We have a at 1, negative 1. We do the same thing for our dilation. It says a scale factor of 2, so we're going to have 1 times 2 is 2, and negative 1 times 2 is negative 2. And we could say, okay, I can see that that point would then be located here, but I don't really like just memorizing how to change the coordinates for a reflection in the x-axis, and I want to see how it works. So reflecting about the x-axis is this horizontal line, and a reflection in the x-axis is going to maintain the distance away from the x-axis. So I can count 1, 2. That was 2 units down from the x-axis. So to reflect it, I'm going to go 2 units up. 1, 2. And that's where the a prime would have been mapped if it was a reflection in the x-axis. So reflections maintain the distance away from whatever axis it's talking about. So this is the x-axis, so it's going to maintain the distance from the x-axis. But a prime wasn't there, so we know that that's not the correct one. So now let's try the other one. A dilation with a scale factor of 2 about the origin, followed by a reflection in the y-axis. Okay, so again, I'm going to I can visualize it a lot better when I do the reflection on the y-axis. When on the graph versus just mapping it out in the function form. So I'm going to do the function form for the dilation of a scale factor. So a, again, the coordinates were 1, negative 1. And if we do the scale factor of 2, that means that it is going to be mapped 1 times 2 is 2, and negative 1 times 2 is negative 2. So if we were to dilate it, a would be located right here. And now to reflect it about the y-axis, okay, so reflection preserves distance, and it's from the y-axis. So the distance from this point is away from the y-axis is 2 units. 1, 2, it's 2 units to the right. So to reflect it, I'm going to pick it up and move it 2 units to the left. 1, 2. Okay, so after the reflection, this is exactly where a prime would land, and it does. So then I want to check and make sure that b prime and c prime and d prime land the same way. So we're going to map out in function notation the dilation, and then the reflection just visually. So the dilation for B's coordinates are at 3, negative 1, And to dilate it by a scale factor of 2, we multiply both coordinates by 2. So 3 times 2 is 6, and negative 1 times 2 is negative 2. So then this only goes to 4, so I'm going to say 4, 5, 6. So this is 6. And it's down 2. So that is where B would be after the dilation. And then again, the reflection preserves distance. So B would be 1, 2, 3, 4, 5, 6. It would be 6 units to the right after the dilation, and to reflect it, we're going to preserve that distance on the other side of the y-axis. So 1, 2, 3, 4, 5, 6, and it does land where B prime is. So 2 out of the 4 is, we're doing well. And then C. C's original coordinates are 3, negative 3. And to dilate it, we're going to multiply it by the scale factor. So 3 times 2 is 6, and negative 3 times 2 is negative 6. So where would that be after the dilation? So we would be at 6 and negative 6. We would be right here. And now for the reflection, it preserves the distance from the y-axis. So 1, 2, 3, 4, 5, 6. So since it was on the right side, we're going to reflect it to the left side, and it's going to be 1, 2, 3, 4, 5, 6. It is that same distance, and that is where C prime leaves. C prime lands. And one thing that I've noticed is anything that lands on the y-axis when you're reflecting it about the y-axis will stay on the y-axis. It can't move left or right because it's on the y-axis. But we can check the dilation. So the dilation for point D, the coordinates are 0, negative 3. So to dilate that by a scale factor of 2, we multiply by each side by 2. So 0 times 2 is 0, and negative 3 times 2 is negative 6. So let's check. It would be at 0, negative 6. And is it reflected about the y-axis? Yes, because it's still on the y-axis. So that is what transformations mapped trapezoid ABCD to trapezoid A prime, B prime, D prime. A prime, D prime, C prime, D prime. Okay, so question 4. Use the following regular polygon to answer the question. How many lines of symmetry does a polygon have? Okay, so I'm going to go back to our lesson 5 notes in the review theorem and look for lines of symmetry. And I'm noticing a regular polygon right here with a lot of lines of symmetry through it, and it says, in fact, for any regular polygon, the number of lines of symmetry is equal to the number of sides it has. Okay, so let's count the sides. There's 1, 2, 3, 4, 5, 6, 7. So there are 7 lines of symmetry since this is a regular polygon. And I'm going to do question 3 because it's a click and drag, and just so you're clear on how to navigate a click and drag. So the coordinates of the vertices of trapezoid ABCD are point A is at negative 1, 4, point B is at 0, 2, point C is at 1, 2, and point D is at 2, 4. ABCD is first rotated 90 degrees clockwise and then translated 3 units right. Match each coordinate to the final image A double prime, B double prime, C double prime, D double prime in the right column with its correct vertex in the left column. Okay, so I'm going to use this graph. so I want to be able to see them. And so ABCD is first rotated. Okay, so A is at -1, -1, 4. Okay, so A is right, -1, 4. There's A. B is at 0, 2. C is at 1, 2. And D is at 2, 4. So the trapezoid here is formed right here. Now it wants us to rotate it 90 degrees. So what I'm remembering from lesson 3, or not remembering if I need to use it as a reference, so go back to lesson 3 and go back to rotating. There's the writing math, and it gives kind of the shortcut of how to rotate a point counterclockwise about the origin. So the first thing that we need to know is that it says rotate a point XY 90 degrees clockwise, which is not what we're doing. So then I'm going to look for the other 90 degrees. It says rotate a point XY 270 degrees clockwise or 90 degrees counterclockwise about the origin, and then it gives us our mapping x comma y and our coordinates negative y comma x. So what that means is that the y coordinate 4 becomes the x coordinate. So the first transformation being rotated, the y coordinate would become negative, and it jumps to the new x coordinate, and the x coordinate stays the same, is in the y coordinate place. So after it being rotated 90 degrees, A would be located at -4, -1. So A would be located right here. So that means if I drew a line from A to the origin and from the origin to A prime, that angle right here would be 90 degrees. So then if I were to draw a line from B and make it 90 degrees, it would end up right here. So because we don't have a corner to pick up and move, I guess, I'm going to use the algebra way, or just remember that the y coordinate, so for B prime, the y coordinate now becomes our x coordinate, and it's negative, and our x coordinate became the y coordinate. So that's the first transformation being rotated 90 degrees. So we're going to do the same thing for C. The y coordinate is negative, and became our x1, and then our x switched places. And then D, the y coordinate, is now in our x place and it's negative, and our x is now in our y place. So that is just after it was rotated 90 degrees counterclockwise. And then translated 3 units right. So now what would happen, I'm going to map these. I'm going to map these new points in magenta at -4, -1. There's A. B is at -2, 0. C prime is now at -2, 1. D prime is now at -4, 2. So there's our new trapezoid after it's been rotated 90 degrees counterclockwise about the origin. And then now it needs to be translated 3 units right. So what that means is let's pick it up and move it 3 units to the right. So now A double prime would be 1, 2, 3. I apologize, this would be D. This is A, B, C prime. So this now, D prime would now move 3 units to the right, and that becomes D double prime. C prime would now move 3 units to the right. 1, 2, 3. B prime and A prime. 1, 2, 3. So now here's our final trapezoid. And if you don't have graph paper and you're a visual person, I would highly recommend using graph paper. The other way we could do it is by algebra. Because it says right, that means we're talking about the x-axis. So we could have come here and said, okay, A double prime, we're translating it 3 units right. So we're adding 3 units to -4. So what is, I'm going to do the work down here so I have room. What's -4 plus 3? That equals -1. So we have -1, comma, and our y didn't change. And so then we could do the same thing to B prime. The x coordinate is -2. We're going to add 3 to it, which is equal to 1. So then our B double prime coordinate is going to be 1, 0. Our C double prime is -2 again plus 3, which equals 1. And so it's going to be 1, and our y coordinate didn't change. And then our D double prime is going to be the x coordinate plus 3 units because we moved them right. So that was along the x-axis. So -4 plus 3 is -1, and that our y coordinate didn't change. So now we have our A double prime, B double prime, C double prime, and D double prime. So A double prime is -1, -1. So you click on it and you drag it. Say you accidentally linked it to the wrong one. You just click on it, not directly on the text, but you just click on that box and it will unlink it. So then you click -1, -1. B's coordinates were at 1, 0. C double primes coordinates, we're at 1, 1. And D double primes coordinates, we're at -1, 2. So there is how you do the click and drag. And if you need graph paper, then use it as a resource to do your transformations instead of just doing straight algebra.